if I wrote down 2 to the power 3 multiplied by 2 to the power 4, like we've done our indices together, what would this be equal to?
2.
Good. Yeah, because you just simply add together the powers. Now here is the idea. Here is the idea. If I wrote an equation like this down, okay, 2 to the power of x equals 16. What would x be equal to?
4.
It would be equal to 4. How did you know? How did you know that x was equal to 4?
Because 2 to the power of 4 is 16.
Yeah, absolutely right. So you're saying, just by trial and error, or hopefully by recognition, you recognise that if you raise 2 to the power of 4, in other words, you 2 times 2 times 2 times 2, multiply together 4 times, you should be able to get to 16. So let's actually think about what is happening here. We would call this an exponential function, okay? Now actually exponential functions are a type of growth. Now it can also be a type of decay as well, but if we deal with the growth case, then that will give you everything you need to understand in order to understand the decay case as well, because it's just in the opposite direction, okay? So what is an exponential function? Well, it's a type of growth which is really, really rapid, okay? So, I mean, there are other types of functions. There are, for example, polynomial functions. Okay, so polynomial function would be something like this. For example, y equals x squared. Okay, so polynomial function. In other words, the power is the constant and the variable that I'm raising it to is the thing which is changing. So let's think about this. If x equals 0, what would y be equal to? If it's a polynomial function, y equals x squared.
1.
Sure about that?
0.
It's 0 squared, right? So it's going to be 0. Okay, so y is equal to 0. Okay, if x equals 1, what would y be equal to? Yeah, if x equals 2, what would y be equal to?
4.
If x equals 3, what about y?
9.
Okay, so it's growing pretty rapidly. What about x equals 4?
16.
16. So it's growing pretty rapidly. It's definitely growing. But the thing is, an exponential function is growing even quicker. Okay, you notice this goes up by 1, this goes up by 3, this goes up by 5, this goes up by 7. What do you think the next one's going up by? 9. So it's going up by the odd numbers each time. Okay, so you're still going up by a linear amount each time. It's a linear sequence which is happening between those. Let's think about this one then. So if I just rewrite this, let's try y equals, what do I have, 2 to the power of x. Okay, let's think about what happens for different values of x. So if x equals 0, what would y be equal to in this case?
1.
Is equal to 1. Anything to the power of 0 is always 1. Okay, what about x equals 1? What would y be equal to?
2.
And if x equals 2, what would y be equal to?
4.
Okay, so can you see that so far you're getting a similar kind of thing which is happening over here? But let's see what happens if I raise it to the power of 3. What's y going to be equal to?
2 times 2, 4, 7, 8.
Good. And if x equals 4, what would y be equal to? 16. Okay, so let's think about what's happening here. You remember up here you were going up by a linear amount each time. Okay, so plus 1, then plus 3, then plus 5, then plus 7. So really it's still a linear sequence which is happening there because you're going up by a fixed amount each time. It's just the odd numbers. Okay, but let's think about what's happening to get from one number to the next. Okay, what are you doing to get from here to here? Times 2. What are you doing to get from here to here? Okay, now this is the pattern for a exponential function. It's basically you're multiplying by the same amount each time. Now if I try and put this into context, what I'm saying here is that x could represent your time. Okay, so whatever time you're at, let's imagine you have a growth, okay, and let's suppose at the start when x equals 0, let's say y is our population. Okay, so the size of our human population at the start is 1. And then we start breeding with ourselves. So after 1 minute, how many people are in the population? 2. And then after 2 minutes, how many people are in the population?
4.
And then after 3 minutes, we've got 8 people. After 4 minutes, we've got 16 people. Okay. Now you notice that this is a type of function which we see in nature. Okay. Think about like bacteria and rabbits and things like that. Okay. Also radioactivity. So basically, whenever you have a situation where every single minute, second, year, whatever it is, you're multiplying by the same amount each time, that is what we classify as an exponential function. Okay? So now let's suppose that I ask the reverse question. At the moment what I'm saying, oh by the way, do you see where this 2 is buried in this function? So the 2 is buried in here. Okay, that number there is always what you're multiplying by. So if I change that to a 3, all that will happen is now you multiply by 3. If I change that number to a 10, all that will happen is that every second you'll multiply by 10. Does that make sense? Okay, so that base, if you like, is what you're multiplying by each time. Now let's suppose I ask a slightly different question. The question I was asking before was, I give you a time, I give you an x value, you tell me what the population is, you tell me how big your population is. Okay. Right, so let's do the reverse situation then. So let's suppose I tell you that y is equal to 1. What would x have to be equal to? 0. If I told you that y was equal to 2, what would x have to be equal to? If y is equal to 3, what would x have to be equal to?
What did you say?
Sorry, what am I doing? If y was equal to 4, what would x have to be equal to?
2.
Okay. If y was equal to 32, what would x have to be equal to?
6. No. 5.
It's 5. Yeah, good. If y was equal to 256, what would x have to be equal to? Let's see who knows our powers of 2. It's 8. Okay. So it's 8. But the point is, it's still perfectly possible because what I'm doing here is just simply taking the whatever root. Okay. So my question is, how could we do this in general? How could we find the time? In other words, I say your population is equal to 256. Find me how long you've waited to get to that point. Okay, we need a way of doing that. And the answer is in logarithms. What I'm literally asking there is, if I give you y, could you find x? The answer to how to do that is through logarithms. So a logarithm is just simply a way of rewriting our equation such that the power is the subject. Okay, so if I say that 2 to the power of x equals 16, that's what I started with. Could I rewrite that in such a way so that x is the subject of the equation? In other words, I tell you that your population is 16, you're multiplying by 2 each time from 1, how long have you waited in order for it to get to 16? And the way which we write it, it's just by definition, is we use x, so we go x equals, we then use a logarithm. Now a logarithm is just simply a function which allows us to rewrite this thing. The base, the multiplier, the thing we're multiplying by each time, in this case is 2, goes down here, okay? And then the size of the population, which in this case is 16, goes in there, okay? So all I've done is I've taken this, which we're familiar with, and I've rewritten it in such a way so that the power is the subject of the equation. That's all I've done. Okay. So in general, if I give you something like this, a to the power of b equals c. Okay, a to the power of b equals c. Good. So the b is the subject. I want to rewrite it to the logarithm. Well, the thing which I'm multiplying by has to be the base. So it goes down here of c like that. Is that okay?